By the end of this lesson, you should be able to identify the period and frequency of a sinusoidal wave. We're going to begin this lesson with some definitions first. The period of a wave is the amount of time it takes to complete one full cycle. While the period talks about how long it takes for a wave cycle to complete, frequency instead talks about how many wave cycles can be completed in one unit of time. For the purposes of Algebra II, unless specified by the problem, our notion of the unit time is 2 pi, as it takes 2 pi radians to traverse completely around the circle in angular fashion. We'll begin by looking at the relationship between period and frequency algebraically. Starting with our base sinusoidal function of y equals sine theta, we have two properties, or really transformations, that we can now talk about. The first, amplitude, was covered in an earlier lesson and sits as a constant multiplier in front of the function. Frequency, however, shows up as a constant multiplier for our input theta. Effectively, by changing our input from 1 theta to some greater multiple of theta, we are asking for the function to evaluate changes in theta at a higher rate. By increasing this constant, the wave happens more quickly, and thus it can happen more frequently in the same span of time. Likewise, if we introduce numbers whose absolute value is between 0 and 1, it'll have the effect of slowing the wave down. The last thing of note here is that period is not actually observable directly from the function notation, but it can be calculated as the reciprocal of frequency. Here, we use 2 pi as a numerator because, again, we're talking circles right now. The graph for this lesson is expanded a little more from the previous lessons, with our theta axis now extending to 4 pi instead of just 2 pi. Starting again with y equals sine theta, we can see the period of 2 pi, as that shape is one full sine curve and it happens in the span of 2 pi time. Even observing multiple cycles of this wave, if we don't adjust its frequency, it will still take a total distance, or really time, of 2 pi radians to complete one full wave. But what if we don't want that 2 pi period? If we look to change the period of our waveform, we bump into a slight issue at first. In order to adjust the period, we need to reconsider that frequency is the input value that we can adjust, and we have to calculate that from the given period. In this case, we want a period of 1 pi. Through some algebraic symbol manipulation, we can ultimately determine that the frequency can be calculated as 2 pi over the period. So here, when we want a period of just 1 pi, we wind up with a frequency of 2. Looking now at the plot of sine 2 theta, we see that the wave occurs twice as frequently, and so therefore its period is half as big, or in this case, 1 pi. In this last set of examples, we're going to readjust our axes back to showing only between 0 and 2 pi radians. In each of these graphs, starting with sine of 2 theta, we'll just take a look at how increasing the frequency has the effect of compressing the wave. Take note that one full wave cycle, here highlighted in this hot pinkish color, doesn't always sit cleanly at the indicated markings along the axis. When dealing with weird multipliers in front of theta, you may need to do some investigative work to accurately work between frequency and period. Also, watch how these graphs are drawn. I set these graphs to take exactly 1.5 seconds to draw between 0 and 2 pi. As frequency increases, you can get a feel for how the curve has to sort of move more quickly to compensate. As this wraps up, I'd just like to remind you that if you have any questions, comments, or concerns, you can feel free to express those thoughts.